Now's our chance to start solving some differential equations with initial values. So if you remember, differential equations have derivatives in them. We're going to have an equation that is a solution. That equation generally, usually, typically has a C in it. It's a family of equations that works as a solution, or a family of solutions. Now, if we want a specific or a particular solution, we need an initial value. I'm going to show you how to start using that. So another thing at this time, some of you might be wondering, how do they get that? Where do you get that? That's like the rest of this course on how to find that, okay? Right now is we kind of start at the back end and go, how do you check it? We're starting with checking it. How do you find a particular solution? We need initial value. So I'm going to show you how to do those things, and then after that, we start with techniques on how to find the actual solution from the differential equation. It's not that bad, but we have to know what to do with it once we get there. So let's start with this. There's really 3 steps on how to find some particular solutions to a differential equation. Step 1, find, if you can, your solution. If it's given to you, that just means you need to verify it. So verify that this actually works there. If not, then none of this actually matters. So verify that this works there. Next, you're going to be given an initial condition. So this starting spot. Use that to solve for C. And then once you have, all you have to do is replace the C right there. So I'm going to show you how to do that on like 6 examples. The first 3 I'm going to do completely for you. The next 3 I would like to do for you to do on your own. Practice this stuff. They're a little bit more advanced, but you should have the hang of it by the time we finish these 3. So step number 1, let's verify it. Let's make sure that in this first order differential equation, this is actually a solution. What that does, remember the last video, we have to take the derivative, thankfully only one of them, and plug it in to see if it works. So if we take the first derivative, C is a constant. It doesn't have any x's in it, so it's just a number. That means that we don't have a product rule here. All we have to do is keep the C, do this chain rule. Derivative of 2x is 2. Just multiply in the front and you're good to go. Now let's plug this in. We're going to take our first derivative. We'll see if that's equal to 2 times our original function. Yeah, that's like immediately apparent that those are equal. So we know for sure that that's an actual solution. We've just verified that that's a solution to that differential equation. Step number 2, once you have verified that, solve for C. This is how you solve for C. So we're going to take and plug in y of 0 equals 3. Now what that means is that y of 0, what's y of 0? Well, y of the independent variable x equals this number. So replace x with that number, replace y with that number, and see what happens. So I'm going to start you off here. Let's replace x. Even shows us what this is. It says if you put in 0 for x, well, it's going to be equal to 3. So if you put in 0 for x, it's going to be equal to 3. That's what that means. Replace the x with this number, replace the y with this number. That's exactly what that means to do. And that allows us to solve for C. Since we replace all the x's with 0 and all the y's with 3, C equals 1/3. Now, man, we're almost done. All we've got to do is replace the C in our original equation, our solution equation that we verified, with whatever C you found. So we are going to have y equals 1/3 e to the 2x. Let's walk through some terminology just to make sure you know what's going on, okay? That's a differential equation. It's a first order differential equation. This is a solution because we verified it. We know that that's a solution. It's a general solution because it's got that arbitrary constant in there. So this is a family of curves. Every single value of C is going to satisfy that. That's crazy. What we're looking for is, now that we know that this is a solution, well, what's the solution? What's that curve that goes through that point? Is that a point? Yeah, that's the point 0, 3. So notice, if you have a family of curves, they look like this because they're exponentials. If you have a family of curves, or like this, if that c is negative, all those exponentials, well then, if you have all that, what's the one of them that goes through 3, 0? And that's what we're asking. Oh, this one. That goes through that point, 3, 0. That's what we're doing. Differential equation, solution to a differential equation, a family of solutions, a general solution here. If we have an initial condition, initial value problem, that limits it, that says you need to find the one of them that goes through that specific point. And that's what we do. We solve for C, and now we have a particular solution to that first order differential equation. That's got to make sense. Before we go any further, that's got to make sense. Let's try this one. So this says, hey, we've got a first order differential equation. This one's different because it's got an x in it. Don't let that worry you. All you're going to do is the same exact thing. Find the first derivative, plug in the original to make sure that it actually works. So verify it, and then use your initial condition to solve for C. So we're finding the first derivative to use here just to verify it. This is going to be reused in our equation that we're checking right now. So the first derivative, chain rule gives us negative c e to the negative x plus 1. This goes to 0. We're going to check this with our original in our differential equation to verify that this works. So on the left-hand side, we're taking our first derivative. What we just found equals x minus our original equation that we just took the derivative of. And we're going to simplify this to see if what they've given us is actually a solution. It doesn't make sense to start plugging in initial values if that's not a solution. It's because then you'd say, oh, this is not a particular solution to that differential equation. That is a waste of time. So we're going to make sure this works. If we distribute that minus, we get x's are gone. These are gone. 1 equals 1. We nailed it. That is a solution to that first order differential equation. Now what we have to do is just solve for C. So we're done with the differential equation part. We're not even looking at that anymore. We've determined that this is in fact a general solution to it. It's got an arbitrary constant. We only need one arbitrary constant with that. It's a first order, one arbitrary constant. All we have to do now is, now that we've verified it, plug this initial condition in and solve for C. So I'm going to rewrite what we're doing here. Our solution, our general solution, is this. Our initial condition, we know that's a general solution. The initial condition, or the point that we need our solution to go through, we have to have it satisfy that. It's going to give us a specific C. All these are different curves. They look like a whole stream of curves on a graph, but only one of those is going to go through that point. The C value is what gives us that one curve that goes to that one point. X is going to become, hopefully you see it, X is going to become 0, Y is going to become 10, and we're going to solve for C. So Y is 10 when X is 0. Usually these work out pretty nice. E to the negative 0, who cares? E to the 0, that's 1. C times 1 is C. Plus 0 minus 1. If we add that 1 over, C equals 11. Let's just replace that, and then we're done. So our particular solution, the solution that satisfies our initial condition from our family of curves here for our general solution to our differential equation is y of x needs to be 11 e to the negative x plus x minus 1. And that's the idea. I hope that's making sense. All right, let's try one more together before I give you like 3 more to do on your own. And then I'll, of course, go through them with you. So we do the same exact process. Let's find the first derivative. Let's plug these both in to verify, and then let's use our initial condition to solve for c. So first comes the verification. We need to take the first derivative to satisfy our differential equation. The derivative of ln of x plus c is 1 over x plus c times the derivative of x plus c. That's a chain rule. Since the derivative of x plus a constant is just 1, remember constants go to 0, we just get 1 over x plus c. Let's plug that stuff in. So we're going to have e to the ln x plus c, that's e to the y equals ln x plus c, times the first derivative of y, we just found that, and that's got to equal 1. Well, if you remember identities, e to ln, that sort of idea, those are inverse functions. Those are an exponential and logarithm are always inverses if they have the same base. That's all gone. We're going to get x plus c. And x plus c times 1 over x plus c, that's certainly going to equal 1. So we know that that's a solution to that differential equation. Now we're going to use our initial condition. So I'm going to rewrite it. So we have our general solution, it's got a c in there. Plug in your initial condition. When x is 0, y is also 0. So 0 has to equal ln of 0 plus c. 0 has to equal ln of 0 plus c. We have 0 for y, we've got 0 for x. So that looks weird. So 0 equals ln c. Let's do an exponential on both sides. Or just think about it. What value of c does there need to be there in order for ln to equal 0? ln of what equals 0? We go 1. Yeah, c is going to be 1. If you need the exponential, e to the 0 equals c, do a e on both sides, or think about the inverse of ln, it's an exponential. E to the 0 equals c, c has to be 1. Which means now we go back and we just replace our arbitrary constant with something that's not arbitrary anymore. Something that's particular, something that says, hey, you're going through that point. You don't need an arbitrary constant. You have a specific constant that's going to let you go through that specific point, that initial condition. And that constant is 1. That's the way that we do it. Verify, solve for c, then just rewrite it. I'm going to erase the board. I'm going to put 3 more on the board for you. I would really encourage you to try them. See if you can verify, solve for c, rewrite. It's not that hard, but the process is important because we're always doing these 2 things when dealing with initial value problems later on. The verify part, well, you're not going to verify anymore in a little while. You're going to be actually solving this. You go, oh, I solved it. Now solve for c. Now rewrite it. That's the way it works. So now that you have the hang of it, try these 3 problems. Yeah, they're a little bit more intimidating. There's more stuff going on, but don't worry about it. See if you can verify first. Take the appropriate derivative, plug it in, see that it works, and then use the initial value problem. Some of you are probably thinking, but I trust you. I'm kind of, yeah, that's just true. I can just see it. Why don't I just plug that in there and find C? You can do that. You can find C that way. It's just good practice to verify it to make sure it actually works. Because if it doesn't work, then that's irrelevant. So try it. Even though it seems like we're kind of wasting time because you're like, well, if they're telling me that's a solution, they're not. They're saying verify that it is first. Trust me, that's a lot easier than finding that yourself. So finding that with the techniques later on take a lot more time. So verifying is way quicker than actually finding the solution for yourself. So take the time to do it. Verify it's actually a solution. Then solve for C, and then rewrite it. So I'm going to start right now. Hopefully you'll take the time to do that on your own. Step number 1, we're going to find derivatives for everything because they're all first order differential equations. That's kind of nice. Now what we're noticing here though is there's got to be a product rule when you're finding that first derivative. Here's a function of x. Here's a function that has x in it. We're going to have a product rule. So derivative of the first times the second plus the first times the derivative of the second. Now the derivative of the second, derivative of a constant, that's 0. So that it's not 1, it's 0, it's gone. The derivative of ln x is 1 over x. So that's what we're going to be plugging in here. Let's go ahead and do that. So when we verify this, we're going to take our first derivative, put it here, take our original function, put it here, and just see if it works. Notice how that's x squared. And notice how this is going to distribute to all of this. This is all the first derivative. It needs to be in brackets. Let's distribute. Let's see what happens. If we distribute this, we're going to get 3x cubed times some nasty stuff that we don't really want to look at, plus x cubed. But here when we distribute, we get minus 3x cubed, nasty stuff that looks exactly like the other nasty stuff. I like that. Equals x cubed. And we can see just on some observation here that this and this are gone. X cubed equals x cubed, and we win. So we know that this right here is a general solution to that differential equation. Now it's appropriate to find C. It might seem pedantic, it might seem like a waste of time. I know it would have when I first took it, to think like, well, it's going to be a solution. But it's important to verify that. So when we plug in, we know that when x is 1, y is 17. Well, so 17 equals 1. 1 cubed is 1. ln of 1 is 0. We just talked about a little while ago. 0 plus c is c. So c equals 17. That's it. Now, all we got to do is replace that with 17. And we're done. We've taken a general solution with an initial condition and found a particular solution to that differential equation. That's it. Okay, next up, we're going to take the first derivative to make sure that we verify that this is actually a solution here. Wow, that's crazy. Do you remember the derivative of tangent? I hope you do. Derivative of tangent is secant squared, but then we have a chain rule involved in that. So secant squared of the original stuff times the derivative of the inside stuff. The derivative of this is 3x squared plus 0. Derivative constant 0. So this is 3x squared, and we're going to put that in front of secant squared of this stuff. So we would get secant squared, leave the inside alone, times the derivative of the inside. That's 3x squared. That's it. Now, plug that in. 3x squared, secant squared, x cubed plus c equals, on the right-hand side, we have some more things going on here. We're going to have, let's see, (3x squared), so that's good. We have y squared, so all of this squared so tangent squared, why? Because that's y. So y squared, take this stuff and square it. Tangent squared of x cubed plus c plus 1. That doesn't look the same. Well, we have to remember some of our identities. So some trig identities are that that works. So secant squared x equals tangent squared x plus 1. What that means is that this right here is really secant squared x. That plus 1 disappears because of our identity, which means that these things are identically the same. This is secant squared x cubed plus c. This is secant squared x cubed plus c by that identity that I just showed you. So that verifies that this is a solution to that first order differential equation. Now it's on us to find c and then rewrite our original solution as a particular solution. So let's do it. We got y of 0 is 1. That means that every time x is 0, y is going to equal 1. So 1 equals tangent of 0 cubed plus c. Okay. What value, what's it take, what's c got to be for tangent of that value to equal 1? I'm thinking, got to be pi over 4. So c is pi over 4 because tangent of pi over 4 is 1. Now we rewrite. So we're here, remember I rewrote it, I always rewrite them, I verify, then I solve for c, I always rewrite, and then at the end I just replace the c. So that is a particular solution. Notice how solving for c gets rid of our arbitrary constant. We're good to go. That's what we're talking about. That's a particular solution. If you have it, man, I'm really going to just beg you to try that one on your own. I'm going to erase a little bit, give you some time to pause the video. Try it if you haven't already. So here we are. Let's take our derivative, let's plug it in, let's verify first. Let's solve for c second. Let's rewrite it last. Again, we have that product rule going on. There's a function of x times another function of x. The derivative of the first, the derivative of x plus c is 1. 1 times cosine x. And then we're going to take the first function, x plus c, times the derivative of the second. Well, the derivative of cosine x is negative sine x. So I'm going to put minus derivative of the first times the second plus the first times the derivative of the second, which gives us that minus there. So that's our first derivative. Thankfully, we don't have to take a second derivative. We just have to plug that in. So if we do that, it says take the first derivative. That's all of the stuff we just did. Plus, okay, so this is our first derivative. We're done with that. Plus take y, that's your original. Multiply by tangent x, and that should yield cosine x. And again, this doesn't look quite right. Well, nothing cancels, Leonard. What in the world are you doing to me here? You need some identities. Because tangent is sine x over cosine x, well, the cosines are gone. We're going to get cosine x minus xc, x plus c sine x, plus x plus c sine x. Those cosines are gone because that's part of tangent. So we get rid of those. We get cosine equals cosine, and that's all you have to do. That's verifying. It's not fancy-dancy. Just making sure that when you plug in the derivative in the original function, that you actually have a solution there. It's a waste of time to do that, to do anything else if you haven't checked that. Now that we've done that, we're done with that differential equation. We have our solution. We know that's it. That's our general solution. We just need to find c. We can always do that with our initial condition. We know that when x is pi, that y is 0. Oops. When x is pi, I guess I should replace all the x of pi. Do you remember what cosine of pi is? So sine of pi is 0, cosine of 0 is 1, cosine of pi is negative 1. So if c is negative pi, we can rewrite our general solution with our c. We get a particular solution to our differential equation. I hope this is making sense. That's about as much as I want to show you on how to find particular solutions given some initial conditions, some initial value problems is what they typically call those. There's one more, it's kind of a weird one, just sort of for fun. Sometimes you'll be asked to do something like find all the values of a certain variable that make this a solution. And we're going to try one of those right now. I think the only reason why I'm doing this is because sometimes you get weird stuff, you're not used to it, you just don't know where to start. Not that it's really hard, it's just you don't know where to start. So how in the world do we find all the values of r that make this a solution of that? Well, just follow the process that we just did, okay? Find the second derivative, plug the stuff in, and then you will eventually be able to solve for r. I'm going to show you with one of them, the rest of them are very similar if you have questions asked of you like this. Let's find the second derivative. The first derivative, remember the chain rule. The second derivative gives us r squared. So first derivative, we get the e to the rx back, but the derivative of rx is r. Do that again. We're just going to get r squared. Plug that stuff in. So 4 times the second derivative equals the first derivative. I'm sorry, I misspoke there. 4 times the second derivative equals the original function. Right, but those are never 0, right? E to any power is never 0. So we can divide both sides by e to the rx, not worry about dividing by 0. These are gone. And if we divide, we're going to get 4r squared equals 1. But wait a minute, couldn't we just do it a number of different ways, I suppose? Couldn't we divide by 4, take a square root, other ways you could subtract the 1, difference of squares, I don't care how you do it. What we've just determined is that the only values of r which give us solutions to that differential equation are when r is 1/2 or -1/2. So hopefully you see what I mean by just follow the differential equation, find the derivatives, plug it in. Eventually the stuff is going to disappear, you'll be able to solve for r. And these are the values that make that a solution of that differential equation. Man, I hope that makes sense to you. So now we should have a pretty good idea about what it takes to solve for a particular solution. It takes an initial value problem for a given solution. So you have to have a solution first. You have to find it or it's going to be given to you. You verify it, so you find it or verify it, plug in the initial value, it's going to give you a particular. Next time we're going to talk about a specific application of this. So I'll see you for the next video when we talk about some time rates of change.